Hello, everyone. I wanted to make a quick video for you to help you with sections 2.2 and 2.3 in Achieve. We got through most of the notes, but we didn't get to some of the stuff at the end. So I wanted to make sure that you had plenty of examples to help you with that homework. So without further ado, let's go. I'll start with these first two. We definitely got through, oh, here we go, sorry. We definitely got through similar examples to this, but we didn't get through these two. So to evaluate a limit that looks like this, what is your first line of defense? That's right. We're plugging it in. Whether it's a one-sided limit or a two-sided limit, right? This is a one-sided limit. X is approaching 0 from the left. It's one-sided, but whether it's a one-sided or two-sided limit, we are going to plug this X value into this function. So we're going to start by plugging 0 in, and we get 0 divided by the absolute value of 0, which is the absolute value of 0 is 0. This is 0 over 0. Okay, so now that we've done that part, we use this for decision making. 0 over 0, what does that tell us is happening on our function? Yes, this is a whole. That means that there's a factor that is making both the top and the bottom 0 at the same time at x equals 0, which means we have a whole there, right? That factor would cancel because it's on both the top and the bottom, making this a whole. Now, limits still exist at wholes. We just have to figure out what that limit is. And this is a one-sided limit, so we only have to make a table from the left, which means we'll pick x values that are approaching 0 from the left. Since we're coming from the left, we're going to pick x values that are a little bit less than 0. So something that's a little bit less than 0 would be like negative 0.1. And then if we get a little closer to 0 from that, we might have negative 0.01. And if we get a little bit closer than that, we get negative 0.001. Now, there's nothing magic about these numbers. It's just kind of easy. And then we're going to take these x values and we are going to plug them into our function that looks like this so that we can figure out what the y values are and we can see where y is going as x gets closer to 0. Okay, so our x value, our first one is negative 0.1, so I'm going to plug it into my function. Y is going to be negative 0.1 over the absolute value of negative 0.1. The absolute value of negative 0.1 is positive 0.1, and this whole thing is negative 1. You can put that in your calculator if you want to, but this calculation specifically isn't too bad. If I go negative 0.01, again on top, I'm going to have negative 0.01. On the bottom, I'm going to have the absolute value of negative 0.01, and I'm going to get negative 0.01 over positive 0.01, and I'm going to get negative 1. And you can see where this is going. The same thing's going to happen with negative 0.001. I'm going to get negative 1. So that means the limit as x approaches 0 from the left, as these goes to 0, these guys are heading toward, yep, negative 1. It doesn't change. It's always going to stay negative 1. That is the limit as we get closer and closer to 0. So this limit, x approaches 0 from the left of my function, that limit is negative 1. All right, the next one, the limit as x goes to 0 from the right of that same function. Again, your first line of defense is plugging this in. We just did this. We get 0 over 0. We're still at the whole, and we're just going to do the same thing, but from the right. So now, if we are approaching 0 from the right, my x values are going to be a little bit bigger than 0. So now I'm going to do positive 0.1, positive 0.01, positive 0.001. We're heading towards 0, but we're staying to the right of 0. All right, and again, we are going to plug these into the same function, x over the absolute value of x. And when I plug 0.1 in, I get 0.1 over the absolute value of 0.1, which is 0.1 over itself, which is 1. And again, 0.01, 0.01 over the absolute value of 0.01 gives me 0.01 over itself, which is still 1. And again, you can see the pattern in what's happening here. If I plugged 0.001, I'm still going to get 1. So as our x values get closer and closer to 0, my y values will continue to stay 1, which means that's the value of the limit as x approaches 0 from the right. So that is the answer to this one. Hopefully that makes sense. Again, first line of defense is plug that x value in, see what happens. 0 over 0 means you're at a hole. A non-zero number divided by 0 means you're at a vertical asymptote, and you're going to make these tables to help you figure out what your limit is, because both in holes and vertical asymptotes, you still have more work to do to discover what that limit is. Okay, and then this not on here, but what if I asked you for the two-sided limit? What would the limit as x approaches 0 of this function be? What if I had the two-sided limit instead of the one-sided? Well, since my limit from the left is -1 and my limit from the right is 1, my two-sided limit does not exist because they don't match. Okay, that's just kind of a fun thing I wanted to throw in there. All right, what if our functions get a little bit more complicated? For example, what if I start having things like this, where I'm adding and subtracting things, or I have things inside of square roots, or I've got exponents? How am I going to deal with these kinds of limits? And as things get really gross? Well, we have these limit laws that are going to help us figure that out. Now, I'm not going to test you on these limit laws themselves as far as what they say. I'm never going to say, tell me what the limit sum law looks like. And I'm not going to make you write all of this out, right? That's not what I'm interested in here. What I am interested in is that you understand what these say and what they mean for limits. And really what I'm getting at with what these guys say is that when you have a limit and your functions get complicated, if you're taking the limit of one function plus another function, you can still find that limit. And as long as both of the limits individually exist, right? The limit as x approaches c of f has to exist, and the limit as x approaches c of g has to exist. Then if we're taking the limit of f of x plus g of x, we can actually distribute that limit across the addition, and we are going to add the separate limits. We can absolutely do that with limits. Everything's going to work the way that you want it to. So if you're taking the limit of the sum of two functions, you're going to add their limits together. And similarly, if you are subtracting two functions, it's not written in here, but if that addition were subtraction instead, right, if you had f of x minus g of x, again, you would just subtract their separate limits. You would take the limit of f minus the limit of g. We also have a constant multiple rule. The constant multiple says that if you have a number times a function and you're taking the limit of that, you're going to take that number and you're going to multiply it by the limit of the function. You can basically pull numbers out of the limit. With a product law, if you're multiplying two functions together and you're taking the limit of that, then you're going to do the limit of the first one times the limit of the second one. It's going to work just the way you want it to. If you are dividing two functions, you can do the limit of the top one divided by the limit of the bottom one, as long as the limit on the bottom does not equal 0. That's what this part says. Because we can't divide by 0. That's the one thing that we have to be careful of. And then the last one are powers. If you have powers like an exponent, if you have a fractional power, which gives you roots, or if you have a crazy looking power that's basically both a normal power and a root simultaneously, you can bring limits inside of those roots. Um, so again, I'm not going to ask you to reproduce any of these definitions, but what these all are getting at and what their powers combined allow us to do is that limits are going to work exactly the way that you think it will. If you're adding two functions, you add their limits. If you subtract two functions, you subtract their limits. If you're multiplying your function by a number and taking the limit, you can just multiply that number by the limit of your function. You're multiplying two functions, multiply their limits, dividing two functions, divide their limits, bring limits into and out of functions. Everything's going to be very intuitive and you're going to do exactly what you think you're supposed to do. So, what if I get really mean? And instead of giving you a graph like we've had, or instead of giving you an algebraic function like we've seen, I give you two pieces of information. All I tell you is that the limit as x approaches 0 of the function f is 4. And the limit as x approaches 0 of g is -2. That's all you know. You don't know anything else about either of these functions, just those two pieces of information. Well, that's enough to do any of these limits that I have here for you. If I want you to find the limit as x approaches 0 of f of x plus g of x, well, our limit laws that we had up there have told me that if I'm adding two functions and taking their limit, I can essentially distribute that limit over the addition, and I'm just going to take the limit of each of them separately. This is the same as the limit as x goes to 0 of f plus the limit as x goes to 0 of g. The limit as x goes to 0 of f of x, we have it right here, that's 4. Plus the limit as x goes to 0 of g, we have that one right over here, that's -2. 4 plus -2, that's 2. That is the value of this limit that we were given. You're going to do exactly what you think you should do. If I had given you something like this without any additional coaching, most of you would have just done this because that's what your intuition tells you that you should do, right? So I want you to follow your gut on these because it's going to pull you in the right direction most of the time. All right, so what about this one? Again, with no coaching, what do you think you would do? How would you take the limit of 5 times f over g? Well, you can bring that limit in and kind of do what you think you should do. We're going to take 5 times the limit of f. We know that the limit of f as x goes to 0 is 4. And we're going to divide by the limit of g. And we know that the limit as x goes to 0 of g is -2. You're just going to plug your limits in. And we're going to get 20 divided by -2, which is -10. And that is the value of this thing. If you weren't sure where I got this from, if that's unclear to you, again, we're going to do the limit at the top divided by the limit at the bottom. And we can apply that limit to basically everything in here. And if I have a number times a function, I can basically pull that number out of the limit, and we ended up doing this. All right. So what if I'm multiplying these two functions, f times g? What's the limit as x goes to 0 of that going to be? Well, since I'm multiplying these functions and taking the limit, I'm going to multiply the limits of those functions. So I'm going to take the limit as x goes to 0 of f, which is 4. And I'm going to multiply it, because that's what we're told to do here, by the limit as x approaches 0 of g, which is -2. And I'm going to multiply those together and get -8. And how about this last guy? How do we do this one? We're going to do the limit of f on top, which is 4, divided by the limit of g, which is -2, plus that 2 here. And we're going to get 4 over 0. Notice now we're stuck because the limit law says that we can use this quotient law as long as the bottom's not 0. But in our case, Ooh, that bottom goes to 0, which means that quotient law lets us down. Right? We can't just divide these because the bottom goes to 0. We know that we are at a vertical asymptote on this function because I have a non-zero divided by 0, but I don't have enough information to go further, right? Um, at these, I don't have this one filled out on these specific notes. We did this one in class where if you plugged that 2 in, you got 1 over 0. That told us we were at a vertical asymptote, and we made our table to tell us, kind of like we made tables here. Um, and so normally we would make those tables, right? But I don't have functions to plug into. I can't make tables because I don't have enough information. So I don't have enough information to finish this problem. And that's all I would want you to tell me is that, look, I tried, I did what I could, but I don't have enough information to do this because I know I'm at a vertical asymptote. The answer is going to be infinity, negative infinity, or DNE, but I would need to make a table or look at a graph to figure out which one of those is the correct answer, and I don't have it. Okay. And finally, if things get really scary here, basically you are going to stick to what we know. Your first line of defense with limits is to plug it in. And depending on what you get out of your function, if it's just a number, you're going to say, yes, that y value is my limit. Nothing weird happens at this point. My y value is my limit. Thank you very much. Put a box around it. Keep going. If you get 0 over 0 or a non-zero divided by 0, you're at a weirdo. You are at a hole or a vertical asymptote, and you have to make those tables to help you figure that out. And no matter how scary your function looks, your first line of defense is to plug in your x value. So let's just do this. Even if we have a bunch of things added or subtracted, those limit laws say trust your gut, plug that number in and evaluate that at each piece. And we're just going to add or subtract or multiply or divide all of our pieces together. It's going to work the way you think it will. So don't overthink it. Plug it in. So I'm going to plug x equals 2 into this function. So I'm going to get 2 to the third plus 5 times 2 plus 7. I'm going to plug it in and see what happens. When I do this, 2 to the third is 8 plus 10 plus another 7. That's going to give me 25. That's a y value. It's a number. Nothing weird happens. My y value is the value of my limit, and we're good. Put a box around it and move on. Now let's try this one. All right, we're going to plug it in because that's what we do with limits. We're going to take x equals 2 and plug it into that function. And we get the square root of 2 to the third power plus 4 times 2. And when we do that, we are going to get the square root of 2 to the third is 8, plus 4 times 2 is 8. We're going to get the square root of 16, and the square root of 16 is 4. Again, that's a number. We're not at a weirdo. That y value is our limit. And even when things get scary, stay the course and do the arithmetic. We're going to plug this in. We're going to get 3 to the negative 1/4 times 3 plus 5 to the 1/3 power. We're going to plug it in. Now we just have to evaluate this. If you put this into your calculator as is, it would probably spit out a decimal at you. And if Achieve says give an exact answer with symbolic notation and fractions, basically anytime Achieve says symbolic notation and fractions, it does not want a decimal that has been rounded. So if your calculator gives you a decimal with lots and lots of decimal places where you have to cut it off somewhere, Achieve won't take it. It's going to want you to give it an exact answer with fractions and roots and whatever else you need. It does not want a decimal. So let's say this was one of those problems and I can't just put this in my calculator and give it a decimal. Now we have to actually figure out what exponents do and remember how to do all of this. Okay, 3 to the negative 1/4. What does a negative exponent do? What is that negative going to do here? Well, negative exponents give us a reciprocal. So that negative is going to throw the 3 to the 1/4 to the bottom of a fraction. That's what a negative exponent does. It pushes you across the division bar in a fraction. And this one already has a positive exponent up here, so it's going to stay on top. It doesn't have to move. So I'm going to keep that 8, right? I just simplified 3 plus 5 to the 1/3 power. I'm going to keep it on top, and I'm going to put it over 1 so that my brain keeps track of what's on top and what's on the bottom in these fractions that are being multiplied. So I have 8 to the 1/3 over 3 to the 1/4. Can I simplify this at all? Now we have to figure out, what do fractional exponents do? Well, fractional exponents give us roots. So if I have x to the a, that's an a, over b power, this b on the bottom creates your root. So we're going to create a bth root. That b is the index of your radical. And the exponent on top is, for lack of a better word, a normal exponent. So you can either put that exponent inside the radical with the x, or you could put it on the outside of the radical like this. So in our case, if we do this, 8 to the 1/3 power, this 3 on the bottom is going to create a cube root. And inside, I'm going to have 8. And then you can either put the first power inside or outside. I know what 8 to the first power is, so I'll just leave it inside. And then similarly on the bottom one, this 4 is going to create a 4th root. And inside, I'm going to have 3 to the first power. So I'm going to have the cube root of 8, which is 2, over the 4th root of 3, which is not pretty. So I'm going to leave it as the 4th root of 3. And this is what I would put into achieve. I wouldn't put around a decimal. I would leave it just like this and enter it with fractions and roots. All right. So that's what I got for you to help you with your homework. Sections 2.3 and 2.4, sorry, 2.2 and 2.3. There we go. 2.2 and 2.3 are combined in one homework assignment, and that's going to be due on Monday, January 13th. I hope you guys have a safe and lovely snow day tomorrow. Stay safe out there, and there's no better time to do calculus homework than when you're inside in a warm place with snow outside. So I hope you have a lovely snow day. I hope you get a lot of calc homework done, and I will see you next week on Tuesday.